talk today, Zoom has spoken. So the talk I'm going to be giving today is titled "Large Explosive Eruptions May be Dominated by Pyroclastic Flows instead of buoyant plumes." Now, I'm sure a lot of you in this audience will probably think, what does that mean? Because you may see the explosive eruptions and think, well, okay, that makes sense. There's a picture of a volcano on the screen. But other than that, what are you on about, Alice? Well, if I was to rewrite that title in more general terms, it's where does the mass erupted during an explosive eruption go? So it comes obviously out of the volcano. We see it. It creates these beautiful plumes. But where does all that material go? And that's really the question that's at the core of what I'm going to talk about today. And so to make sure that we're all on the same page before we start, there'll be some terms that I use quite frequently in this talk to describe the different phenomena and different ideas. But I appreciate not all of you will be familiar with these terms. And so I want to make sure that we're all on the same page and you understand what I'm talking about when I refer to them. So, of course, explosive volcanic eruption is fairly self-explanatory. These are the most violent and energetic expressions of volcanism on Earth. So the ones that are associated with big bangs, big ejections of material, very dramatic, very explosive, as the name would suggest. Next is pyroclastic flows. Some of you may be familiar with these. These are the very ominous looking clouds of ash and gases that roll down the sides of a volcano during an explosive eruption. There's been footage circulating on social media quite a lot, and you see these flows kind of very ominous looking. I think in one of the more recent Jurassic World films, Chris Pratt attempted to outrun one. Spoiler, you can't do that. They're very, very fast. But that's the kind of phenomena that we're talking about when I say pyroclastic flows. A buoyant plume, that's the vertical part of the eruption. So this is the cloud of, again, ash and gas that goes upwards towards the atmosphere and creates these incredible pillars that go high up into the atmosphere. The ignimbrite is the geological term for the material that's laid down by a pyroclastic flow. Because as you can imagine, when you have all that material rolling down the volcano, it ends up settling on the ground and it settles in these layers. And over time, these become compacted or welded because of the super high temperatures. And this is called an ignimbrite deposit. And so when we describe the geological record and we describe past pyroclastic flows, they're described as ignimbrites. And then the ash is the term for the very, very tiny microscopic materials that come out during an explosive eruption. So you could hold it. It looks a bit like sand when you hold it in your hand. It's very, if you kind of throw it up in the air, it can be quite smoky. It's very, very bad to inhale because it is so small. And like the description says here, it's fragments of rock, mineral crystals, and glass. All things that are created as magma when it is erupted during an event. The magma, so the liquid, sort of molten material, fragments or shatters because as it comes up, it cools down when it reaches near the surface of the earth, shatters very, very fast. And that creates these glassy particles, almost as if you were to throw a cricket ball at a greenhouse. You know, you've got that very fast shattering of glass. Same sort of effect here, but with magma that's being erupted during a volcanic eruption. And so just for some visuals to accompany these descriptions, explosive eruptions, these are the kind of things we're looking at. So very dramatic, very awe-inspiring, not the kind of thing you'd want to be stood right next to, but equally incredibly beautiful. So we've got two examples on the left here from South American eruptions, from the past 10 years or so. And then on the one on the right is the infamous ejecta eruption in Iceland that happened in 2010. I'm sure many of you will remember the disruption that that event caused, but we'll talk about that eruption a little bit more later on. These are the pyroclastic flows again. So you've got the same composition. You've got the gases and the ash and solid materials, but instead of going upwards into the atmosphere, they roll down the side of the volcano. Buoyant plumes, so the vertical ascending phenomena that go up into the atmosphere. You can actually see with this this beautiful image here where the plume has encountered the upper layers of the atmosphere. So And you can see where all the very complicated physics and chemistry is going on here to create this gorgeous looking umbrella type. And the same here, these umbrella cloud type features. And just to give you an idea of how high these buoyant plumes go, this is a diagram of the atmosphere. So this shows how the red yellow line is temperature. So this is how the temperature changes as you ascend up through the atmosphere. These are the heights of certain volcanic plumes that we've witnessed in recent years, of course, apart from Tambora, unless any of you are alive in 1815, which I consider highly unlikely. But this is when you compare that to the height of Mount Everest, you just see just how high these are going. And the Hunga Tonga eruption of 2022 is a very special case because this was actually the highest ascending eruption plume that we've ever directly recorded with satellites. So you can see the image here that was taken. We were incredibly lucky, actually, that the satellite was passing over the volcano at just the right time to capture this image. And then this is Pinatubo here, and then the Tambora caldera here. Again, we don't have any photos of Tambora, given that it was quite a way ago now, before satellites, before fancy cameras. Ignimbrites. So this is what an ignimbrite deposit typically looks like. So you can see it's quite compacted, welded material, quite distinct as well in the rock record. You can sort of see here you've got different fragments or plasts in there that have been entrained by these incredibly hot cascading sort of waves of material. And they can be really huge and really quite spectacular, as this picture in the right-hand side shows us. On the complete opposite side, ash is incredibly small. So this is what I mean when I say it looks a little bit like sand. Then you can zoom in and you can see the glassy texture of the particles and shards that are in there. And actually, this photo was taken as part of my undergraduate research, where we went up to a peat bog in Carlisle and we took a long section of peat material and burnt away all the organic matter and sieved it. And what we found were these glass shards, most likely from Iceland, dating back about 2,000 years. So these glass shards can travel very, very far, and they can be preserved for a very, very, very long time. And so it's become clear in both recent history and also looking further back into the past that volcanoes are not only present on every continent, but they are a continuous feature of our planet. They shape how our planet appears to us and how it's appeared to life on Earth throughout geological past. And it happens, along these tectonic boundaries. So you can see what we call the Pacific Ring of Fire as you come around here. The Daily Mail love talking about the Pacific Ring of Fire because it sounds really dramatic. It basically just means there's tectonic boundaries where volcanoes can exist and where explosive eruptions can happen. Then you also have distinct geologically anomalous regions, or even just along these sort of slightly secondary margins here. But the problem is, as we go further back in time, start to try and understand how volcanoes have shaped our planet further back into the past, our records become quite sparse, and there's a lot that we still don't know about particularly the largest eruptions that have happened in the geological past. And I guess the statement at the bottom sums it up perfectly. We've never directly studied an eruption exceeding a magnitude of 7. Now, I'm sure you're probably thinking, well, how does a magnitude 7 relate to anything that I know? How actually big is that? So we're going to do a quick comparison. So we'll start with a magnitude 4. So that is comparable to Le Soufriere eruption in 2021 that some of you may have seen on the news. That's a magnitude of 4. And then every point increase you go up in this scale, it's called a logarithmic scale, which means that the volume, so the amount of mass that's erupted during the event, increases by 10 times. So magnitude 5 is 10 times bigger or more voluminous than magnitude 4. So an example of magnitude 5 is the eruption of Mount Vesuvius. So the famous Pompeii eruption in 79 AD. 10 times bigger than Vesuvius was Pinatubo in 1991. Some of you may remember, some of you may not. This happened in the Philippines. This eruption has been fundamental to helping our understanding of large explosive eruptions. But that was magnitude 6. But as many Hollywood films say, there's always a bigger rock, there's always a bigger eruption. Example of magnitude 7, so 10 times bigger than Pinatubo, Santorini. So the Santorini eruption, the Minoan eruption, it's also known, referred to as. But then 10 times bigger than Santorini. So the eruption that essentially blew out this huge caldera that you can see from space and that forms the island of Santorini today, 10 times bigger than that was the Toba eruption. A side note, Toba is my favorite volcano, and it's actually the volcano that got me interested in volcanology in the first place. But I'll save the anecdotes. This was a magnitude 8, potentially even a magnitude 9. And that potentially is important because this eruption, as you can see, happened a very long time ago. And given that our geological records become more sparse further back in time, this magnitude is very much an estimate and very much an underestimate. It is more likely this eruption was nearer a magnitude of 9, given the amount of material that was likely deposited in the sea, which means it's a lot harder to find and to quantify. Some other examples of some magnitude 8 sort of volcanoes that have produced magnitude 8 eruptions. Some of you may be familiar with, and maybe not aware that they are supervolcanoes, or these called supervolcanoes. So you'll hear the term supervolcano. Basically, this means a volcano that's produced a magnitude 8 eruption. So a well-known example is Taupo in New Zealand. So Lake Taupo is actually the caldera of a supervolcano. Lake Atitlan in Guatemala has become very popular with tourists in recent years. That is also a supervolcano and the caldera of a huge volcanic eruption. Yellowstone, how could we not mention Yellowstone? Perhaps the most famous of them all. Aso in Japan, the entire city you can see here is built inside the caldera. And then you've got these sort of more recent, or at least more primitive volcanoes in the middle. And then perhaps less well known is Cerro Galán in Argentina, a bit more remote up in the high Altiplano region. But these are all volcanoes that have produced these, and known to have produced these huge magnitude 8 eruptions. And you might think, well, a lot of these eruptions happened a long time ago. Why should we care? Well, we should care because we need to understand how eruption dynamics, or in other words, how eruptions evolve and change and what their hazards are, and how that may change depending on how big the eruption is. And also explore the impacts of volcanism on the Earth prior to humans coming along, because I think we're all very aware by now that humans have altered the Earth system in huge fundamental ways. But in order to understand how that influence is going to force our future, we need to understand what the Earth system was doing before we came along, so we can get almost like a baseline level or background level. And volcanic eruptions are a huge part of that and a fundamental part of that. And just because we haven't observed a really big eruption doesn't mean that one won't happen again in the future. In fact, it's inevitable another one's going to happen again in the future. And so if we don't study them, how are we going to know how to respond and how to build strategies to cope with that when that does happen? And like I mentioned before, we have learned such a huge amount from more recent events like Hunga Tonga, like Pinatubo, like Eyjafjallajökull. But there's a key question that remains unanswered, and a question that we really do need to answer. And it's, are the largest eruptions fundamentally different from the smaller events that we've witnessed in recent history? So in other words, do the impacts of volcanism just simply get bigger with magnitude? And that might sound like a bit of an obvious point. You know, you just think, well, magnitude, surely a magnitude 8, you just get the same as a magnitude 4, but bigger, and there's more of it. Well, there have been several lines of evidence suggest that might not actually be the case. But before we dive into that, I'm going to quickly give you an overview of how we understand volcanic eruptions, or how our understanding has evolved. Now, I'm not going to go into all the complex math because there's a lot that goes into this, and I don't want to send you all to sleep on this Wednesday evening. But the crux of this is that the first model that was proposed to explain how volcanic eruptions and plumes behave, so how the mass behaves once it's been ejected out of the vent, was in the 1950s, where they used observations of simple plumes, so like smoke plumes coming out of chimneys, for example, and came up with the basic physics to explain those. But the problem is that volcanic eruptions and volcanic plumes are very, very different to smoke plumes because, for example, smoke plumes are created by fire. Volcanic plumes are not created by fire. They're created by explosive fragmentary processes. And so there's different physics going on there that can't be explained by that very, very simple model. And so this very simple model was then developed by two sort of canonical, like seminal pieces of work, who essentially suggested that as you increase the amount of mass that's projected out of the volcanic vent during an explosive eruption, you essentially get to a point where the plume is so heavy it can't be held up by the atmosphere by the atmospheric pressure. And so it essentially collapses on itself and caves in and rolls down the side of the volcano. And so the atmosphere, and that's what we call the point that the atmosphere can hold the plume as the point of neutral buoyancy. So the plume is buoyant, and then it can flow through the atmosphere. What we're talking about here is a case is where when you've got so much mass, it's too heavy for that to happen, so it collapses and comes down the volcano. Now, of course, that makes you immediately think to these very, very large eruptions in the geological record, and you think, well, the most voluminous eruption, surely that could explain their behavior. You know, do they collapse on themselves too, given that even though they have a lot of mass, can they not produce these tall plumes? And so to kind of summarize everything I said there, volcanic eruptions produce these jets of gas and solid particles that entrain heat, they entrain atmospheric air, and they become buoyant to the point where they rise. So then, like I mentioned, we have the buoyant umbrella cloud, which is like the pictures we saw at the beginning, where you've got that very tall column, and then it spreads at the top to create this sort of mushroom shape. But then you also have the collapsing pyroclastic density currents, where the heavier components collapse in themselves and roll down the side of the volcano and coat the environment, with ignimbrites, those deposits. However, the plume models that I described before and geological evidence suggest that actually these really big eruptions might partition their mass in a different way to smaller eruptions. And the plain English way of saying that is they may have different amounts of mass being deposited as pyroclastic flows compared to the ash plume. So, for example, there's evidence for eruptions where you've got these huge ignimbrite sheets covering hundreds of square kilometers, but very little evidence for ashfall that would suggest there was a buoyant plume that could be carried with ash that could be carried far away. Equally, more sophisticated models have shown that when you reach this critical threshold, also the mass eruption rate, so this point of sort of the heaviest point of the plume, that they become unstable and can't hold their own weight, so collapse. And also volcanoes that produce these very big eruptions tend to have a very different architecture or subsurface architecture compared to smaller volcanoes. And so that might mean that you might have an eruption that is not just one single vent producing a tall plume. It might be several vents across a longer latitudinal, or at least sort of horizontal plane, where you've got multiple eruptions happening at once. You might have different magma batches. So, for example, underneath the ground, we don't always have one huge body of a magma chamber. There might be lots of different magma chambers that all go off at different times. And that might affect then how the mass is erupted from a volcano too. So all these factors combined suggest that actually the biggest eruptions on Earth may not simply just be bigger versions of smaller events. So, for example, the Toba eruption, like I mentioned, might not just be a very, very big Eyjafjallajökull or Le Soufrière, for example. So answering this question is something that we need to do not only for our understanding of geological past, but also our understanding of future hazards posed by volcanism too. So what did we do? Well, we compiled evidence across or at least we went through the literature and tried to compile as much information as we could on volcanic eruptions that have been studied and their deposits mapped and characterized from a broad range of locations, magnitudes, tectonic settings. So from our compilation, we collated data for 74 eruptions. You may think that doesn't sound very much. I'll explain why that number isn't higher in a second. But just as a small note, the two eruptions mentioned on the screen now are the smallest eruption in the compilation, so the Eyjafjallajökull eruption of 2010, and the La Garita eruption in Colorado, which happened about 28 million years ago. So we really covered a broad temporal range, or tried to cover as broad a range as possible to encapsulate all different magnitudes of volcanism. So the data set was constructed in two stages. So at first we took all existing well-established databases of volcanic activity and looked at all the eruptions in there, because that gives us an idea of which eruptions are known to have happened. And then once we've been through there, we could start eliminating eruptions based on the information that was available to us. And that was done as part of the quality check. And so it wasn't just enough to extract the data from the databases. We had to go through manually and check that all the volume estimates that were provided for each eruption were correct, that they were cited across multiple studies. So it wasn't just one study saying, oh, I found this quoted a number and that's it. You know, we wanted to make sure that the studies were consistent in the volumetric estimates for each event. And this is a map that shows the volcanoes that we're able to include, or the source volcanoes we're able to include, so covering a broad latitudinal range. The only continent we couldn't cover was Antarctica, and that's because the volcanic record on Antarctica, as you can imagine, because it's such an extreme environment, is very, very difficult to characterize. And as a result, there were not many volcanoes that could meet our criteria for inclusion, so they didn't have much information that we could go off. And so, building on what I was just saying, the number isn't higher for the number of eruptions that we could include, because a lot of them, A, didn't have robust estimates for the total deposit volume, but also the volume of this mass that was characterized as ash or ignimbrites, because those are critical pieces of information we needed to figure out where the material was going during each specific eruption. We also eliminated eruptions if the literature could not be transparent with how they treated their data and how they treated the errors in the data. Because of course you can quote a volume estimate, it might not be correct. There are errors, so you need to say it's this number, give or take. If studies weren't transparent about this or didn't say how they came up with these calculations, we didn't include it because we didn't want it to affect our results. And also we didn't include eruptions that were known to have produced two different kinds of volcanism, termed hybrid eruptions. So a good example of this is the Timon Fire eruption of Lanzarote. Also, the Cumbre Vieja eruption in La Palma is another example of a hybrid eruption where you had both explosive phases, but also effusive phases where you had these lava flows gently cascading out over the landscape. And these are very complex eruptions. And so for us to characterize explosive events, the total volume wouldn't have been representative of the amount of material explosively ejected. And so we didn't include those eruptions for this particular compilation. So on to the results, which is the most exciting bit. What our analysis showed is that we have a significant negative relationship between eruption magnitude, so how voluminous the eruption is, and the ratio of fall deposits to the total volume, which in simple terms means that as the eruption magnitude increases, the amount of its material that's deposited as ash or fall deposits decreases. And so that suggests that the bigger eruptions are ejecting more of their material as pyroclastic flows to eventually become ignimbrites compared to ashfall. We also found when we interrogated our data set further that as you move further away from the ocean and to volcanoes that are inland, this relationship becomes significantly stronger. And so a reasonable explanation for this is that these eruptions are generally better mapped, better characterized, because you've got less material being deposited into the sea. When you have eruptions, say, for example, like Tambora, which is in Indonesia, so surrounded by water, you have a lot of material that's being erupted, but then deposited into the sea, both the ash deposits and the pyroclastic flows. Marine expeditions are very, very expensive. Mapping submarine deposits is very, very difficult. And so there are much greater uncertainties in the volume estimates. And so if we account for that and start removing eruptions from the database by moving further away from the ocean, you have the strongest relationship with the inland volcanoes, which suggests to us that this relationship is solid and that the slightly weaker relationship, so the 0.2 relationship here, is being slightly diluted by eruptions with much larger uncertainties on their volume estimates. And so, of course, ideally, we'd have, all 74 eruptions would have perfectly characterized volume deposits, but volume estimates, but this, of course, isn't the case. And the difference between the two plots here, distance is basically as the crow flies, distance from the vent that erupted to the nearest ocean. And dPDA is distance if you follow the primary dispersal axis. So essentially the direction the plume went when it was erupted based on the wind direction at the time. And that's the distance from the vent to the ocean if you're traveling in that trajectory. And so our results collectively suggest that the largest explosive eruptions are fundamentally different from the smaller events. And you'll see on the left here, here's a diagram that illustrates this, this phenomenon quite nicely. So you've got here the smaller eruptions with the buoyant plumes, you've got the vertical ascending component, and then the plume goes high into the atmosphere and then can be dispersed by atmospheric circulation. You get to the big eruptions here where the plume is just far too heavy. It's projected up by the energy of the eruption, but then immediately comes back down and flows out onto the landscape, covering the landscape with ignimbrites. And so knowing this and taking this result, we now can ask, how does this finding, or how could this finding affect us and our planet? Number one, it could influence how significantly the climate is impacted following a volcanic eruption. So volcanic eruptions release lots of gases, and one of them that's particularly interesting to us is sulfur dioxide, which is erupted up into the atmosphere. It interacts with the oxygen in the atmosphere to produce what we call sulfate aerosols. And these aerosols, once mingled with the atmosphere, they alter how heat from the sun is absorbed into the atmosphere and then absorbed at the surface, or the thermal budget, so how heat is exchanged between the Earth and space. It influences that. It influences the composition of the atmosphere and also the motion of the atmosphere. So the sulfate aerosols prevent heat from getting in. It means that more heat is absorbed in the upper atmosphere, meaning there's less heat coming down to the surface, which means that the surface actually cools down. It also affects the motion of the atmosphere because we have what's called the intertropical convergence zone, which is the tropical rain belt that extends all the way around the equator. If you have a volcanic eruption, for example, in the northern hemisphere, the tropical convergence zone will move away from the aerosols. It'll be forced away from that, from the sulfate. And so what happens there is it alters the distribution of rain at the Earth's surface. So you may have regions becoming drier or wetter, depending on which hemisphere they're in. And so applying that to our result, our data suggests that if you've got an eruption that's producing more of a tall plume that can reach the upper atmosphere, these might be the eruptions that inject the most sulfur dioxide into the atmosphere and so produce more significant or severe climate disturbances in their aftermath. Whereas the really big eruptions, even though it's been assumed for a very long time that these eruptions could cause, in quotation marks, volcanic winters, actually, if you've got this absence of a very tall plume that's effectively delivering sulfur to the atmosphere, you might actually have a more muted climate impact than you may expect from these very, very large eruptions, simply because the sulfur is not getting to the upper atmosphere where it can then be climatologically significant. And so here are some images that illustrate the effect that so these sulfate aerosols can have on our planet. And so some of you may recognize the Scream by Edward Munch on the left. The funky looking colored skies here are supposed to be have been inspired by the aftermath of the Krakatoa eruption, because sulfur aerosols interact with the atmospheric gases to produce these very spectacular optical effects. You've got the Little Ice Age here. You've got a picture of the Thames when the Thames froze over, which we now strongly suspect was caused by a cluster of volcanic eruptions occurring just before the Little Ice Age that essentially caused a long-term cooling trend and anomalously cold temperatures. And these two pictures here, these are both from the Pinatubo eruption in 1991, which resulted in a net decrease in planetary temperature of about 1.5 degrees. So the whole planet cooled by about 1.5 degrees. And you had this, again, these incredibly funky looking skies, the optical effects. And so how else could our findings be important? Well, it could also influence how we perceive and anticipate volcanic hazards, because on a global scale, the risk assessments that we have used to, I guess, to inform our response to volcanism have focused mainly on these super eruptions, these massive events that were thought to have caused volcanic winters and societal collapses and all these big dramatic effects. But if these large eruptions don't produce buoyant plumes in the way that the smaller eruptions do, we probably can't just scale up the effects associated, that we typically associate with smaller eruptions. So, for example, the two pictures I've included here, we've got Mount Vesuvius on the left, in the backdrop of Pompeii, but then we have the Campiflagray supervolcano caldera that Vesuvius sits on the margin of. Now, our data suggests that actually we can't understand or anticipate how an eruption of this caldera could appear and manifest based solely on studying Vesuvius. It's just that the two are completely, even though they're in the same region, they're in the same place. It's just that they could be fundamentally different in how they appear at the surface, and therefore they would be associated with completely different hazards. And so what it also suggests is that the economic repercussions of volcanic eruptions may not scale with magnitude. So the most expensive eruptions might actually not be the biggest ones. And so to illustrate this point, I've just compared some recent eruptions. The 2010 eruption in Iceland cost the global economy around about $5 billion in the context of aviation cancellations, trade was disrupted, huge knock-on effects to the global economy and globalization of our planet. Whereas this eruption was 2 orders of magnitude smaller than Pinatubo and Hunga Tonga, which cost still a lot, of course, but nowhere near the same extent. And so one reason for this, of course, could be that these 2 eruptions occurred in different places. For example, Eyjafjallajökull occurred in the North Atlantic trade route, and so it was in the prime location to be disruptive, whereas Pinatubo and Hunga Tonga are over in Asia, where there aren't as many of these global pinch points. But the problem is, of course, I've got arrows pointing to different eruptions and different magnitudes, but then we've got this whole class of eruptions down here that, yes, they happen more rarely, but that doesn't mean they don't happen. And so what would the financial repercussions of one of these eruptions be? And actually, would it be dependent on where one of these eruptions happened? So, for example, if you had Campiflagray erupt in Naples, would that have the same economic effect as if you had for example, Toba erupt in rural Sumatra, for example? But then you've also got to think of factors like, for example, yes, you might have these very extensive pyroclastic flows, but would the climate impact be enough to disrupt global food production? Or would actually we need to be more concerned about these smaller eruptions that are actually more frequent? And so more opportunity for disturbance and disruption. So it's all things to think about of whether we've actually been too reductionist in how we've perceived these hazards of volcanism, and actually whether we need to consider if the eruptions we need to be concerned about are actually the smaller ones, because not only are they more frequent, but they may actually have effects that can be much further reaching than these large eruptions that have been given a lot of media attention in recent years. And so to summarize, I guess the key points or key take-home messages that if you were to go away from today remembering these, I would be very, very happy. So our data compilation reveals that ultimately, as the eruption gets bigger in terms of volume, the amount of material deposited as ash decreases relative to this volume, which means that there's more of the erupted mass going as pyroclastic flows rather than these tall, buoyant plumes. And so ultimately, this challenges the intuitive assumption that the largest eruptions will produce the biggest, most catastrophic, most deadly effects. Actually, it might be a case that the smaller eruptions are the ones that we need to be most concerned about. And this is knowledge that will ultimately help us try and predict and mitigate the impact of future eruptions of all different magnitudes in a highly and increasingly globalized world. And before I finish, I just want to quickly give a sort of special thanks to a few people who, without their insight, this sort of work would not have been possible. Of course, my collaborator, Fabian Wadsworth, who is my co-author on the paper that accompanies this research. He was fundamental in getting me to do this study and write it, and his insight has always been so invaluable to me. Dr. Rich Brown at Durham, Thomas Aubrey at Oxford, Sir Steve Sparks, Sam Engwell, Dave Pyle, Johan Gilchrist, Matteo Colombier, Ali Peccia, and of course the Yorkshire Geological Society for their funding. But I think ultimately research like this, it stands on the shoulders of giants, and we're never doing this research in isolation. There's always a team of incredibly brilliant minds and talented people who are willing to give up their time, who enable things like this to happen, and who have influenced me more than I can put into words. So without them, this certainly wouldn't be possible. And without the Yorkshire Geological Society, it wouldn't be possible either. So thank you all so much for coming and listening to me on this Wednesday evening. And I welcome any questions or any comments that you may have.